What if I told you that the ultimate speed limit of the entire AI revolution, every generative video, all those massive language models, the whole trillion-dollar future we keep hearing about, what if I said it isn't actually determined by giant NVIDIA chips?
Right, it's what everyone assumes, right?
Exactly. But what if it's actually gated by microscopic beams of light and the global supply of zinc?
It just completely flips the whole narrative. I mean,
Yeah.
we are so conditioned to think of artificial intelligence as purely a software breakthrough, or, at most, a story about massive data centers packed with processing power.
Yeah, just rows and rows of blinking servers.
Right. But when you look at the raw physical infrastructure, you find this microscopic bottleneck that is structurally incapable of keeping up with demand.
Well, welcome to the deep dive. We are synthesizing a truly massive stack of intelligence for you today to unpack this exact bottleneck.
And we really pulled from everywhere for this one.
We did. We've got technical breakdowns of quantum laser physics from Wikipedia, supply chain forecasts from TrendForce and SemiAnalysis, and a deep financial teardown from Nexus Finance.
Plus some raw intelligence straight from the Q2 2026 earnings transcripts of Macom and Furukawa Electric.
Yeah, alongside some really interesting corporate data from Sivers Semiconductors. And our mission today is to connect all those dots for you. We're going to explore why a specific type of laser made from incredibly exotic materials is triggering a supply chain crisis.
A crisis that tech executives are actually warning will be more severe than the infamous memory chip shortages.
Right. We'll look at the physics of why we need them, why they take years to build, and how the biggest companies on Earth are frantically trying to secure whatever supply they can get.
It is a unique collision of worlds. You rarely see a scenario where the behavior of subatomic particles so directly dictates high-stakes corporate mergers.
So to appreciate the financial panic happening right now, we really have to start with the physical wall the tech industry just hit.
Yeah, the traditional way we move data has fundamentally broken down under the weight of AI.
Let's look at the AI data center. You have thousands of these powerful GPUs, and they have to constantly talk to each other to train a model, right?
Right. They're sharing terabytes of data every single second.
And historically, all that data inside a computer traveled over copper wires. But when you read the Nexus Finance breakdown, they make it incredibly clear that copper is just failing at this new scale.
It all comes down to electrical resistance and, the physical properties of metal.
Because you can only push it so far.
Exactly. When you push data at the sheer frequencies these new AI clusters demand, copper degrades the signal integrity. As the frequency goes up, the electrical current actually gets pushed to the outer edges of the wire.
The skin effect.
Yeah,
Right.
the skin effect, which drastically increases resistance
So it's burning a massive amount of power just trying to shove the electrical signal through the wire.
and generating heat in the process. But more importantly, because of that signal loss, copper literally cannot cover the physical distance required in modern AI pods.
Wait, really? Like it just fades out?
Yeah, you can only send that high-speed signal a few inches before it turns into static. It's like trying to force a fire hose amount of water through a crazy straw.
Oh man, that's a great visual.
Right. The pressure builds, energy is wasted, and barely anything comes out the other end.
So the industry solution to this is optical interconnects. We are swapping out copper for photons, essentially moving data via light.
Which solves the distance and the heat problem.
Right. Now, normally, when the tech world encounters a problem, they solve it with silicon. And silicon photonics are incredible for a lot of things. But there is a massive inherent flaw in silicon when it comes to this specific task.
Yeah. The fatal flaw of silicon is a quantum mechanical property called an indirect band gap.
Okay, break that down for us.
So silicon is a miracle material for routing light, splitting it, modulating it, but it physically cannot generate the photon efficiently.
So it can't make the light itself.
Exactly. When you pump electrical energy into silicon hoping to get light, that indirect band gap means the energy requires a shift in momentum. So instead of releasing a photon, almost all of that energy gets released as a phonon.
A phonon, which is just a fancy word for heat, right?
Basically, yeah. It just gets hot instead of glowing.
I love thinking of it like a highway. Silicon is the world's greatest highway system, complete with exits and overpasses, but it doesn't have any headlights.
That's a perfect way to put it. You can guide the traffic, but it can't create the beam of light to begin with.
Which brings us to the savior of the AI data center, which is indium phosphide, or InP. It's a 3V compound semiconductor, meaning it's made from elements in groups 3 and V of the periodic table.
And the reason we care so much about indium phosphide is that, unlike silicon, it has a direct band gap.
Sitting right around 1.34 electron volts.
Right. And because the band gap is direct, an electron can drop straight down across the energy gap without needing that shift in momentum.
So it doesn't make all that wasted heat.
Exactly. That means the electrical energy is converted directly and highly efficiently into a photon. Indium phosphide can actually act as the headlight.
Okay, wait, I'm stuck on something here, though. Because telecom companies have been wiring cities with fiber optics since the 1980s, right? We've been shooting lasers down cables across the ocean for decades.
Yeah, long-haul fiber is nothing new.
Right. So why are we suddenly acting like building a laser is this insurmountable crisis-level problem? Why not just use the lasers we already have?
Because an AI data center is a uniquely hostile environment. Think about a traditional telecom laser. It usually sits in a nicely air-conditioned server rack, far away from the main processors.
It has room to breathe.
Right. Plenty of airflow. But the AI architecture is totally different. The sources keep mentioning co-packaged optics, or CPO.
CPO, yeah, where they pack everything tight.
In a co-packaged optics setup, you are taking that laser and embedding it millimeter close to the GPU to reduce the distance the data has to travel.
And that GPU is radiating like 700 watts of heat.
Exactly. If you put a standard telecom laser next to a chip running that hot, it would either physically melt, or the thermal expansion would cause the laser's wavelength to drift so violently that the receiver wouldn't be able to read the data.
It would just see garbage.
Just pure static. So they needed to design a laser that could withstand blistering heat without losing its precise frequency.
And that brings us to the two heroes of our story here, the EML and the CW-DFB lasers. TrendForce highlights both of these as critical.
Yeah, they're the only ones up for the job right now.
Let's start with the CW-DFB, the continuous wave distributed feedback laser. How does it actually survive that heat?
So the Wikipedia breakdown of distributed feedback lasers reveals an absolutely breathtaking internal architecture. In a standard laser, you typically have mirrors at both ends of a cavity.
Light bounces back and forth between the mirrors, gaining energy until it shoots out.
Right. But if heat causes the material of that cavity to physically expand, even by a fraction of a nanometer, the distance between the mirrors changes.
Which means the wavelength of the light changes. That's the drift.
Exactly. To solve this, a DFB laser completely removes the end mirrors. Instead, the active region contains a continuous periodic structured element.
But a diffraction grating, right, built directly into the semiconductor itself.
Yes. It makes me think of those rumble strips on the side of a highway, just a continuous series of tiny ridges running through the entire laser cavity.
That visual is spot on. And the sources say it uses a first-order grating with a 1/2 wave periodicity.
Which creates a phenomenon called Bragg scattering. Basically, that means the optical feedback is happening continuously all along the laser, rather than just bouncing off the ends.
Okay, but if you just leave those rumble strips perfectly spaced, the laser has this tendency to jump between two different frequencies at the same time.
Yeah, the physics term for it is degeneracy.
Degeneracy, right. And obviously, if you're trying to send a pure signal, having your laser emit two wavelengths simultaneously is completely useless.
The engineering workaround for degeneracy is brilliant, though. To force the laser to lock onto one single frequency, engineers induced a perfect quarter-wave phase shift right in the middle of the cavity.
They intentionally create a defect in the grating.
Exactly. It's like tuning a guitar string and then placing your finger perfectly on one specific fret to force it to ring out one crystal clear harmonic note.
Oh, that makes so much sense.
That quarter-wave phase shift creates an incredibly stable single-mode resonance because the frequency is locked by that physical grating rather than just the length of the cavity. When that 700-watt GPU spikes the temperature, the wavelength stays locked.
The data actually survives the heat.
Exactly.
And alongside the CW-DFB, we also have the EML, the electroabsorption modulated laser. While the CW-DFB provides a continuous, steady beam of light that gets chopped up into data externally, an EML integrates the laser and the modulator into one single chip.
Which allows for insanely fast on and off pulsing for the highest speed connections.
But both EML and CW-DFB lasers rely on that indium phosphide base, and both are incredibly difficult to manufacture.
Which brings us to the actual supply chain collapse we're seeing. The sudden vertical spike in demand for AI clusters has completely broken the market's ability to supply these components.
To give you a sense of the scale here, Michael Hurlston, the CEO of Lumentum, he gave a presentation in Paris recently.
And Lumentum is a massive player here. They operate 5 separate indium phosphide wafer fabs.
Yeah, they're giants in this space. Yet Hurlston publicly warned that this shortage will easily surpass the severity of the memory chip crisis.
Which is saying something, considering how bad that was.
He noted their shipments are running more than 30% below what customers are actively demanding, and the gap is just growing.
The historical context here is key. Hurlston explained that in the traditional telecom market, clients would order these specialized lasers in batches of hundreds, maybe thousands.
Right, small batches.
Suddenly, NVIDIA and the hyperscalers, companies like Google, Meta, Microsoft, they're demanding them in the hundreds of millions.
Yeah. TrendForce data backs up that scale shift perfectly. They project that by 2026, the monthly production capacity for EML and CW DFB lasers needs to aggressively scale to 50.7 million units just to keep up.
And right now, 3 companies, Broadcom, Lumentum, and Sumitomo Electric, they command about 55% of the market.
But looking at the financial data, we see a massive anomaly in how the market is treating these companies.
Yeah, the Nexus Finance teardown highlights something really wild. NVIDIA clearly sees this physical bottleneck coming.
Oh, absolutely. So they poured $2 billion into Lumentum and another $2 billion into Coherent, specifically to secure their supply of these lasers.
Right. You would think that having the most powerful tech company on Earth hand you $2 billion would send your stock to the moon.
But instead, Lumentum stock dropped 22% and Coherent fell 37%.
It makes no sense at first glance.
Here's where it gets really interesting. Why is Wall Street punishing the companies making the most critical component of the AI boom?
Because Wall Street isn't looking at the current demand. They are terrified of the capital expenditure, the CapEx, required to actually meet that demand.
CapEx being the money a company spends to buy physical assets, like buildings and machinery.
Right. Building capacity for indium phosphide isn't like scaling software where you just rent more cloud servers. It requires an astronomical amount of upfront cash.
Think of CapEx like trying to build a massive state-of-the-art restaurant chain from scratch across 50 cities while you're currently still just running a food truck.
The upfront cost is staggering.
And investors are worried these companies will bankrupt themselves trying to build the factories before they ever see the profits.
Add to that the timeline, right? Investors know that hyperscalers are impatient. If it takes 5 years to build enough laser factories, Google and Meta might just invent a totally different architecture by year 3.
Leaving these laser companies with billion-dollar factories they no longer need.
Exactly. It's a huge risk.
So why does it take so long? Let's talk about the manufacturing choke point. Why can't a company like Lumentum just rent space at a giant chip manufacturer like TSMC and ask them to run a batch of indium phosphide lasers?
Because the manufacturing processes are fundamentally incompatible.
Incompatible how?
Well, a standard silicon chip factory is called a CMOS foundry. CMOS factories are miracles of scale. They use photolithography, essentially shining light through stencils to print billions of circuits onto silicon wafers.
It's highly automated, like a printing press for computing.
But indium phosphide doesn't work in a printing press. Not at all. You cannot process NNP in a standard CMOS foundry. It requires highly specialized machines.
Right, the MOCVD or MBE reactors, metal organic chemical vapor deposition, and molecular beam epitaxy.
Such a mouthful. Let's focus on the MBE reactor. It is essentially a massive ultra-high vacuum stainless steel chamber. Inside, elemental sources are heated until they vaporize, and then those individual atoms are fired at a substrate.
Wow, so you are literally growing a synthetic crystal atom by atom, one microscopic layer at a time.
Exactly. And you can't just buy an MBE reactor on Amazon. The Nexus Finance report points out that ordering, building, and installing one of these reactors takes 18 to 36 months.
Just to get the machine powered on inside the building.
And once it's on, you face the qualification hurdle. That takes another 12 to 18 months.
Because hyperscalers have to rigorously test these lasers for failure rates, right? Remember, in a co-packaged optics module, the laser is integrated directly with the silicon.
They use something called a photonic integrated circuit, or a PIC.
You can think of a PIC like a standard green motherboard you'd see in a computer, but instead of copper traces carrying electricity, it has microscopic glass-like waveguides carrying light.
And that's exactly the problem. If a hyperscaler qualifies a laser from Lumentum, they design their entire PIC around the exact specifications of that specific laser.
The switching costs are monumental.
Huge. If they suddenly want to use a laser from Coherent instead, they can't just unplug one and plug the other in. They have to redesign and respin the entire photonic circuit.
So we are looking at a 3 to 5 year lead time to actually increase the global supply in any meaningful way.
Which is an eternity in tech.
So looking at this landscape, the companies involved are being forced to pick distinct survival strategies. Let's look at how they are reacting. You have the outsource strategy, like Sivers Semiconductors.
Sivers is a merchant supplier in Sweden. They looked at that 36-month delay for new equipment and realized they couldn't scale their own fabs fast enough to capture the current demand.
So they announced a massive collaboration with W Semiconductors, basically outsourcing their high-volume manufacturing.
Right, to bypass the equipment delay and grab market share right now.
Then you have the incremental defense strategy. I found the MCOM earnings transcript absolutely fascinating for this. They aren't spending billions building new greenfield fabs from scratch.
No, they are taking a highly surgical approach to upgrading what they already have. They expanded their North Carolina fab capacity by 30% for under $20 million, simply by hunting down discounted equipment.
And they are systematically upgrading their fab in France to 6-inch wafer lines. But MACOM's real masterstroke was building a moat around their raw materials.
Oh, this is brilliant.
Right. They invested 45 million British pounds into a UK company called IQE. They didn't do it for a quick return on the stock market. They did it specifically to lock down a long-term supply agreement for the raw indium phosphide substrates.
While everyone else is fighting over factories, MACOM is securing the dirt.
Exactly. Then there is the third strategy, which is complete vertical integration. Applied Optoelectronics, or AAOI, is doing everything under one roof in Texas.
They grow the indium phosphide crystals, they fabricate the lasers, and they build the final transceivers.
Because they control their entire destiny, they are sitting on over $324 million in hyperscaler orders right now, guiding for over $1.1 billion in revenue for 2026.
Controlling the full stack in the U.S. is becoming a massive strategic advantage, especially as geopolitical tensions make these major tech companies nervous about relying on overseas supply chains.
So what does this all mean for the big tech companies? If the suppliers are tapped out, how are the hyperscalers making sure they actually get what they need?
Well, you stop waiting in line and you buy the line itself. The urgency has triggered an aggressive wave of mergers and acquisitions.
The M&A frenzy is just in overdrive right now. Elon Musk just acquired Mesh Optical Technologies. Their core product, the Alpha C1, relies entirely on these specific optics.
And he bought them just 4 months after their Series A funding round.
Series A is early-stage venture capital. Companies are usually just starting to prove their business model then.
Musk didn't even wait for them to grow up. He bought the talent and their supply chain access immediately.
But the defining move of this era has to be Marvell's acquisition of Celestial AI.
It's staggering. Marvell paid up to $5.5 billion for Celestial AI.
Now, Celestial has great intellectual property for photonic fabrics, but the financial analysis suggests Marvell didn't just buy the IP.
No, they paid $5.5 billion to get Celestial AI's supply chain qualification stack.
They literally bought their way to the absolute front of the line with the laser suppliers.
And the broader market immediately understood the value of that move. NVIDIA's CEO, Jensen Huang, stood up shortly after and called Marvell the next trillion-dollar company.
When Jensen Huang speaks, Wall Street moves. Marvell's stock spiked 32.5% in a single day, adding over $60 billion to their market cap.
Which is the total value of all their shares.
Their data center revenue is up 27% and now makes up 76% of their entire business. The sheer volume of capital is violently shifting from pure computing power over to the connectivity layer.
There is, however, a fallback scenario that the industry giants are still chasing. Intel and TSMC know this indium phosphide supply chain is a nightmare, so they're trying to bypass the MOCVD and MBE reactors entirely.
Through a process called monolithic integration, growing the laser directly onto the silicon wafer inside their massive standard CMOS foundries.
If they achieve monolithic integration, they can scale laser production infinitely alongside standard computer chips. But the physics are brutal.
You run into something called lattice mismatch, right?
Right. The atomic structure of indium phosphide and the atomic structure of silicon just don't align.
When you try to bond them together, it creates microscopic defects. It's like trying to zip together two zippers with differently spaced teeth.
Perfect analogy. The defect rates are astronomically high, and the technology has been delayed for years. So while Intel and TSMC try to force atoms to cooperate, The merchant laser suppliers hold all the cards.
This physical reality is warping the entire architecture of the modern data center. You see it clearly in the Furukawa Electric Earnings Q&A.
They're rapidly scaling up their water cooling modules and optical cables.
They know the heat from these GPUs requires extreme liquid cooling, and the data demands optical connectivity. The physical layout of the building is literally bending to accommodate the physics of light and heat.
It forces us to realize that the cloud and artificial intelligence are not abstract virtual concepts. They are entirely bound by the physical constraints of atoms, materials, and thermodynamics.
So the next time you use an advanced AI, remember that its speed isn't just a product of brilliant software or massive GPUs. It's physically gated by microscopic, perfectly calibrated beams of light passing through indium phosphide.
The transition from pure computing power to connectivity and networking is the defining shift in tech today.
Which brings us to one final, truly mind-bending fact to mull over. We've talked about the years it takes to build these reactors and the billions being spent by Marvell and Musk.
Yeah.
But the ultimate bottleneck of this entire shortage isn't just about building fabs.
It comes down to dirt.
Exactly. The raw material required to make these lasers, indium, does not exist in standalone mines. It is exclusively a byproduct of zinc smelting.
Meaning the global supply of indium is entirely tethered to the economic logic of the global zinc market.
Its supply physically cannot be independently scaled. It doesn't matter how many lasers NVIDIA wants or how many billions of dollars Marvell spends. You only get more indium out of the ground if the world needs more zinc.
Which is just, it's incredible to think about.
It really is. So the ultimate speed limit of the AI revolution might not be human ingenuity or even the power grid. It might just be the global economic demand for galvanized steel and zinc. Now there's a thought to leave you with. Thanks for joining us for this deep dive.